All right. So, um, I wrote here the mass of photons being accepted is inevitable. To me, it makes logical sense that neutrinos, which we know have mass and travel at ever so nearly the speed of light, should be smaller than a photon. This is because they do not interact with matter very much. Photons, on the other hand, do interact with matter very much. Because of this, they must be larger than neutrinos, or they would not be seen. If they are larger than neutrinos, and we know neutrinos have mass, then so too should photons have mass. They still travel ever so close to the speed of causality and have a tiny mass, but they do have mass. This mass would vary with their relative speed or energy, and so higher energy would mean less mass, as that mass has been converted to energy rather than being matter. This can be seen with hot steam being lighter than liquid water, but having more useful energy, just as a higher energy photon has more useful energy and less mass. A result of a photon entering a material such as glass is that it experiences a greater amount of gravity within the material. This would result in a relative increase in mass and a relative decrease in speed. The energy will remain constant, however. This can be seen as we know we weigh more on Earth than on the Moon or Mars. And also, we know that time travels ever so slightly faster the farther away from Earth you get. So that is because of the difference in gravity. As such, the bending we see of light is a result of a warp in space-time within the material and is not truly bent from the photon's perspective. Now, that part kind of gets a little funky because it kind of is a little weird to think about it like that, but when we are looking at, refraction of like in water, we're observing this bending of space-time. And again, I really want to say, like, realistically, I don't think bending, I think bending and space-time is kind of going to become outdated. If we accept what I have just said there, which again, the evidence is just writing itself at this point. I really don't know why it's not a thing yet, but space-time and the bending or the curvature of space-time is going to go out the window, because really what's happening here is space-time is dark energy. Dark energy is a fluid, and this fluid is flowing. There is no curvature to the fluid. It is just a difference in flow rate. So the closer you are to a mass, the flow rate is stronger. The farther away from the mass you get, the flow rate is slower. And so this difference in flow rate is what we observe as the curvature of space-time, but is why we see curvature in the first place, because as we know in gravity, light travels through gravity, right? And it's going straight, but it's getting pushed down. And we know that in a river, the same thing, the water's flowing, and if you try and go across, you're going to get pushed down, because it is not an attractive force. It is a flow of energy. And everything is getting caught in this current. And so that is why everything falls down towards the mass, because that's where the flow is towards. And that's why we get this strong pressure in the Casimir effect, because the flow of energy between these 2 points is, going into these 2 plates, but once it's flowing into these two plates, then there's nothing there, right? So it's pulling them together. And there's just so many points where we can connect gravity to dark energy and see them both as pretty much one and the same. Well, no, not one and the same, because gravity is really just the flow of dark energy. Dark energy is its own thing, but they are part of the same. They are part of the same thing. I guess I should say they are part of the same thing. And there might be more to dark energy. It might also be time, the flow of time. We know that me talking right now, from like just from the beginning to the end of that sentence, time has passed. And then you notice what I say there, time has passed, right? Because it was this time, now it's this time, right? And it's flowing past us. So again, I think time is a part of this flow of dark energy. And this dark energy, what we're, collecting here is either partially or fully just time. And I'm going to get into that more in my next one, I think. I don't think that's part of this one here. Yeah. Getting ahead of myself. But everything starts to make a lot more sense when you see it that way. And you start to realize how little is missing from the standard model when you start making these connections. Because the thing is you also need to think about the standard model predicts things very accurately, right? On the small scale. And that's because on the small scale, we ignore gravity, but we use dark energy. But then we try and pull gravity into the very large, right? But we also try and use dark energy, and they're kind of, you're overlapping. Like there's a, it gets convoluted. It's already kind of in the equation, except it's not fully realized in the equation. And so that's why it doesn't quite convert well. And that's why general relativity doesn't quite convert well, because general relativity does not factor in dark energy or anything like that. And so it doesn't work well at the very small because of things like that, and probably other reasons too. I haven't gone very hard into trying to figure out how to make general relativity work at the very small. I don't think it's necessary. I think they're basically the same thing. We can bridge them very easily. We just have to realize that things we think are different are the same. So I feel like I'm just rambling. I've lost my, I think I said what I needed to say in that one, and I'm just gonna end it there. So, peace out.